I assume you can all hear me?
Yep.
All right, thank you. Again, apologies for being late. So I'm going to finish up with a little bit of discussion about performance of tries, and then we're going to move on to a new topic, which is large file systems. So we've moved out of the searching and sorting on disk. And so at this point, we have our choice of what we want to talk about. I think large file systems is definitely something that most of you will be interested in, so I'm going to cover that. If out of the other topics you do have any particular interest, you can certainly go ahead and email me and let me know that. The ones that we have are advanced storage systems, so that would include things like how does a solid-state drive work, how does holographic memory work, how does magnetoresistant RAM work. We also have a section on distributed hash tables, which are used for peer-to-peer networking and other things like that. And then we also have a section on things like Mongo, Neo4j, other types of large collection databases which are specifically designed for certain types of data that falls outside of the relational database realm. So. But anyway, let's finish up with try performance and then we'll talk about large file systems. So you remember that I showed you last class that with a try or with a extendable hash table, in a constant amount of time, we can actually look up and as long as we keep the bucket sizes reasonable, search a bucket for a given key, add a key, remove a key from an extendable hash table in constant amounts of time. Okay, so let's just finish up by saying, does our extendable hash table, which we represented as a bucket directory, and you remember that the bucket directory is that array where if you take the hash value and you take a certain number of bits off the front of the binary representation of the hash value, you can actually get a direct access to the entry in the bucket directory, the entry in the array that's actually going to hold the key if the key exists in the table. Okay. So does that satisfy our goal? Of finding key k sub t in constant time. So you remember that what we do is we hash kt to h, and we use the n most significant bits of h as an index I, and then we search bucket a I in bucket directory A for kt, either it exists or not. And so that's constant time. And we saw that insertion may require an expansion, but that only affects a sub I, possibly splitting it. So that's also order 1. And deletion may require compression, but that only affects, again, a sub I, so still order 1. Okay, So at least in this scenario, we're getting constant time performance. There is one thing that I haven't mentioned though, which is that what happens if the bucket directory doesn't fit in memory? Because it's possible, right? So right now we're assuming that the bucket directory fits in memory, but it may not. So you might ask, what if a sub I doesn't fit in memory? That would be the last sort of scenario where we would have to think about, are we actually going to be able to do this or not? Okay? And you've probably already guessed that this is not a problem. It is going to require one additional seek, but 2 seeks versus 1. I guess in some sense you could argue, well, that's twice as slow, which would be true. But in asymptotic performance terms, it's still constant time. Okay? So if a sub I is too big for main memory, we store it as a contiguous block on disk, which is exactly how you would store any array on disk. And given I, we can calculate the offset of a sub I from the front of the file. And we can do that because every entry in ACE is constant fixed size, right? It's an offset. It's probably about 4 bytes wide. And so if you tell me I can tell you from the front of the file where I is going to sit inside there. So we can seek and load a sub I in one seek. And in practice, we normally load as much of A as possible around a sub I with the hope that future searches will also index into this chunk of A, precluding a seek to load the proper part of A into memory. Okay? So, of course, you're not only going to load a sub I into memory, you're going to load as much of A as you can into memory. You're going to have to make sure that chunk of A that you load in has I because you need it. But you're going to try to be smart and hope that future search requests ask for entries inside A that live inside whatever you load in that includes I. Okay? And there's different ways you can try to do this in reality, unless you know something about the predicted sequence of queries that's going to be issued and how those are going to relate to hash values. There's no guarantee that you can load in the proper piece. But let's say you can only load half of A. So you would load, say, the top half or the bottom half that contains I, and then your probability of actually having what you need for the next query would be at worst 50%. So you might argue that you're only making an extra seek every other query. Okay. But even if you aren't, even if you have to load every time, it's one seek to load the piece of A that you need, and then it's one seek once you get that piece and find out where's the offset of the record I'm looking for to load the record. So 2 seeks per query, still constant time. All right. Any questions about any of that? Okay. So I guess what I would say is that we've come a long way from the beginning of the semester where we probably had no idea how to actually efficiently store and retrieve information on disk. And even if we could do that, we didn't expect to do it in any kind of reasonable performance characteristic. But now I've shown you two ways, variations on B-trees and extendable hashing, where you can get either very, very low asymptotic performance or guaranteed constant time asymptotic performance from not only searching, but maintaining a collection on disk. Which I think is pretty impressive, actually. So good work to whoever came up with this stuff. Pippinger and Bear and all of those other people. All right, any questions about just basic searching and sorting on disk before we move off that topic and into something new? All right. So let's talk about large file systems. And I think that I can talk about the new topics in this area in the context of the actual course itself. So 541 and the corresponding undergraduate version, which was 431, I taught for a number of years when I started here. And it was unusual because normally these are not separate courses at that time. They're usually included as part of the introduction to databases, okay? Because databases are the place where you're going to be using B-trees, where you're going to be using, you don't normally use extendable hashing, but B-trees and other things like that. But we had our own course. And so that went on for a number of years, and then it sort of petered out. And one of the reasons why I think is because nothing new was happening in this area. So we knew to use merge sort for on-disk sorting. We knew to use B-trees or maybe extendable hashing for on-disk searching. That had been the case for many, many years. It wasn't changing. And so there really was no need to have an entirely separate course on this. We could include that information fairly efficiently at the front of the database course. And that was where it got put. And I actually think it's still there, in spite of my requests to the people who teach that course not to do that. Nobody listens to me unless I make them. And I don't care enough to make them. And then a funny thing happened. Technology came along that allowed the capture and storage of information in a very cheap, efficient way. And so everybody and their dog started capturing information about how people hit their website and what they did when they were there, what people were buying, what people were paying, whatever your business was, everything that was happening online or in other ways that you could capture electronically about your business you were saving. Okay? And so we got to that inflection point where it was cheap enough and easy enough and convenient enough so that you could just do it. And so people did it. And then the next question came along, well, I've got gigabytes or terabytes of information that I've captured. What do I do with this? And so, of course, everybody's convinced there's gold. There's gold somewhere inside this data, and I just need to find it. And so the fact of the matter is there may or may not be gold. We would have to take a proper sort of structured analytic look at what you have to figure that out or not. Maybe you should be capturing a different kind of data. But regardless, two important requirements came along in fairly recent times, the last 10 to 15 years. One is the need to actually be able to store and query efficiently very large amounts of data, and not necessarily data that's only numeric, okay? So as in many areas, we're very good at numeric and character-based data, okay? The relational database management systems have been handling this forever. We're not necessarily good at things like unstructured text, graphs, images, videos, audio, and other things like that. So new database storage techniques needed to come along to deal with that. The other thing is that we're not necessarily good at being able to actually analyze data that doesn't fit in main memory, okay? Or even analyze large amounts of data that does fit in main memory, because one of our file servers here, for example, has, I think it's 15 terabytes of memory, so we could hold a 15 terabyte data set in theory. Once you get a 15 terabyte data set, what was efficient for a few hundred megabytes or gigabytes is probably no longer efficient. And so you may need new techniques to analyze those. And so part of this is the area of data science, which I work in. That's come along, and so its definition is maybe not entirely set. So you have data science, data analytics, business analytics. We actually ran, interestingly, some analytics, we'll call it, on the descriptions of the programs throughout the country and what they call themselves. So this is what you say your program does, and you call it data science or data analytics or business analytics. And we tried to determine, is there any correlation between what you call your program and what you say you teach? And not surprisingly, the answer is no, there is absolutely no correlation whatsoever. All right. It is true that the business analytics programs tend to be slightly more clustered, but still not to the point where it would be statistically relevant. Okay. So people are choosing random names, in essence, to try to describe their program. And so there are techniques of what I would say statistics, mathematics, and computer science bundled together, most of them from a very practical perspective, to produce this so-called area of data science. Obviously, there is research going on in this area, in areas like machine learning, in other areas in mathematics like time series analytics and predictive analytics. But really, those are the, as with many new areas, it's a combination of things that we already used to do and call something else, being applied in a different way and being researched from a different perspective. Okay. And so large file systems came along because we had this need. And so there was this explosion of new information in the 431, 541 type area, mostly driven by companies, to be honest. And you'll see that most of the techniques that we talk about going forward are all driven by companies like Google or Facebook or Microsoft, okay? Which is not a bad thing. That just happens to be where the initial work was done. And so at some point I thought, oh, there's enough new information that we could actually reintroduce these courses with this new information added, and it might be enough information so that it's not part of the beginning of the database course. And so that's what we've done. So that's why we're moving into these things like large file systems. In fact, it turned out that not only was there enough information to create a viable course, there was more than enough information. And so now we have to pick and choose which of this new information we're going to talk about, because there's more than we can cover in a single course. And it continues to change, so I have to keep the course updated every year because things move very rapidly in this area, as opposed to the old days when nothing ever changed and I could use the same notes every year and nothing needed to be updated. Hold on a sec. There we go. So the lights in here work by motion detection, and if they don't detect me moving for a while, I guess they turn off. And I haven't quite figured out what the difference is between how to keep them on once they're on and how to not keep them on. And so, sorry about that. So that was a sort of blah, blah, blah explanation of the course, why it's back, and what we're doing. Do you have any questions about that before I continue?
So I took the course by Dr. Fry that is basically like enterprise storage architecture systems.
Yep.
So I'm imagining that there'll be some overlap between kind of the latter part of his course and the latter part of this course. But his was more focused on like creating systems? Is this more going to be focused on like, this is how those systems do, I guess, like disk access, more than just like, oh, this is how you create them to apply for like redundancy or high availability with this? Like, is that making sense? I'm not articulating my question very effectively.
Nope, you're articulating very well, and that makes perfect sense. And so yes, there will be overlap in terms of the topic, but I think in terms of how we address the topic, it's going to be different. So for example, we won't talk about how redundancy is provided by the actual disk array system in detail, but we will talk about redundancy and why we care about it. And we're actually probably going to do that today because we're going to talk about RAID arrays, which by their nature are about redundancy.
Cool, thanks.
Okay, other questions about this? And like I said, I'm pretty open to teaching whatever. I might need a few days to sort of get up to speed on it. But if there's some particular topic you're really interested in, you can email me. And if I think, yeah, that would be useful for the class, I'll teach it here. And if I think, yeah, that's probably something that's a little more specific to you, what I'll do is I'll send you some resources so that you can actually get up to speed on it yourself. We're all about the learning. All right, you know NC State's mission statement is to educate the citizens of the state of North Carolina. So we research, we publish papers, we get grants, we do all sorts of other things. But in theory, the thing we're most responsible for is teaching. And I think that's a good thing. So let's chit chat a bit. So the amount of data being captured and saved is increasing very rapidly. So an example is that Facebook estimated they store and analyze, of course, approximately 30 petabytes, where 1 petabyte is 1,000 terabytes of user-generated data. Now, that number was produced back in, do I have it here? No. It's probably about 4 or 5 years old, so it's going to be a lot bigger than that right now. And so the IDC estimated that 1.8 zettabytes, so zettabytes, where 1 zettabyte equals 1 billion terabytes of data would be created in 2011. So that's almost 10 years ago. Okay. And new systems have been proposed to store and manage this data. So we've got issues of efficiency, cost effectiveness, and the types of analysis likely to be performed. These are important criteria for the design of these file systems. So actually, there were file systems prior to these new ones coming online that were specifically designed to store large amounts of data. And so the example I'll give you is National Weather Service. National Weather Service actually runs out of a military base. It's an Air Force base in California where I've actually been. And so their job is to store information, very large amounts of information about weather conditions, many different weather conditions on a very granular time scale, forever, basically. And so if you actually went to their facilities, the way it worked was that there were various levels of storage and accessibility to that. So at the front end level, there was actually a system that had a massive array of hard drives. And I think they had in there 100 gigabytes, which at the time was quite a lot. And behind that, they had these tape packs. And the tape packs stored huge amounts of data. So one of the things, and we actually still use tape packs, by the way. One of the reasons why we like tape packs is because the cost per sort of terabyte or gigabyte or whatever you want to use is very, very low. And of course, the disadvantage of a tape pack is that it's completely linear in terms of how it provides information. Okay, so it's a great storage medium, but it's not a great medium for actually accessing information, especially if you're going to do it in a random access pattern. So what happened there was that the data would go to tape pack, and there were these massive, they look like sort of tubes or chambers. And if you looked inside there, there were hundreds and hundreds of tape packs all around the outside wall, and there was a little robot on the inside. And so when you went to the file system, you would request a file, and the file was in one of two places. It was either cached on this massive disk array that they had, or it was sitting on a tape pack. If it was cached on the disk array, you would get access to it immediately. If it was sitting on a tape pack, what would happen is that an algorithm would run and decide, okay, what are we going to sort of kick off the cache in order to make room for what you're asking for? And then the appropriate cylinder would be queried, and the robot would actually reach in, grab the tape pack, slap it into a reader, and the data would start getting spooled into the disk array, and then at some point it would be there. So when you requested a file, either you would get access to it immediately, or you would wait about 5 to 10 minutes, and then you would get access to it. But from the perspective of your program, the only difference was that you might have to wait or not. You just asked for the file, and it either showed up or it didn't. Okay, so that was a great system. The problem was that if you asked for something that wasn't on the disk array, it was slow. And so most big file systems can't really afford to do that because they can't predict a priori what it is you're going to want to get to, so they don't know how to be smart about what they put on the disk cache, apart from your standard algorithms like first in, first out, last in, first out, etc. Okay, the kinds of things we looked at when we were talking about records. The other thing that was important to the system working well or being appropriate is that out of all of the data that was actually stored, less than, I think, 0.1% of it would ever be looked at, ever be requested. So it's sitting there in case you need it at some point in the future, but it's like a library full of PhD theses. They're there in case you want them, but the likelihood of any one thesis ever being looked at by anybody at any point in the entire history of that thesis is pretty low. All right. So it's a system where tape packs make perfect sense because you're very rarely going to want information out of it. Okay, that's not the case now. And so that kind of system is probably not appropriate for something like Facebook or Google or Apple or Microsoft or Amazon. Because that's not the access pattern that they're actually looking at. Okay, so yeah. So it was an interesting sort of scenario. I went there to visit because that's where one of the high-end visualization groups was for the government, and I wanted to meet these guys. They asked me to come out. But because it was on a military base, and at the time I wasn't a US citizen, there were some issues about me being allowed to get on base. And so what happened was when I showed up at the gate where I was going to be checked in, I had to surrender my Canadian passport, and they would give it back to me when I left. And so the dude that I was hanging out with showed up, and he said, "Did you drive here?" And I said, "Yeah." And he's like, "Okay, I'm gonna have to drive your car. You're not allowed to drive on base." And I'm like, "All right." So we got in, we drove for a while, and he was all super, super like sort of formal and rigid and all that. And then at some point he totally loosened up, and he was all like, "Hey man, what's going on?" and all that. And I said, "Okay, what just happened there?" And he said, "Well, we've moved far enough away from the main base that the guard towers can't see us anymore. And so we're cool." Like he says, "Don't do anything crazy, but we don't have to be so formal about everything." I had this massive red badge that took up like half my chest, which basically said, "If you see this person walking by themselves anywhere, like basically shoot them or detain them or something." And so, yeah. And they told me this funny story about one of their own workers and how serious things were there. So they said their friend, their colleague, was sitting in his office, and he's working away, and two suits show up, and they're from the security group, not good. And they're like, "Hi," and he's like, "Hello," and they're like, "Come with us." And so he gets up, and they go to somewhere, and they put him in a room. They lock the door, and they leave. And he sits there for some reasonable period of time, concerned about, why am I locked in a room and what's going to happen to me? And so the guys come back at some point, and they said, "Hey," they said, "we were just curious. Why are you getting email from Cuba?" And he's like, "I'm not getting email from," and then he thought for a second, and he remembered somebody in Cuba apparently knew his wife and couldn't get a hold of her through email, didn't have her address, so they sent an email to him and asked him to pass it along, which he had done. So he explained to them, "Okay, this is what happened." And they're like, "Huh," and they left and locked the door. He sat there for another long period of time thinking, "I'm probably going to see Cuba in the live." And they eventually showed back up again. And one of them said, "Okay, so we took a look at your story, and we took a look at things online, and we think we might believe you." And then the other guy says, "But you understand, right, why you're never, ever going to get email from Cuba again?" And the guy was like, "Yeah, I understand." And they said, "You can go." And so he left. And of course, when he got home, he just blew up at his wife, and he was like, "You almost got me killed. Like, don't be having any of your Cuban friends send me email." And so I don't think that happened again, but yeah. So it didn't matter whether you're a US citizen or not. Military base, so yeah, don't be getting emails from Cuba or North Korea or anything like that. So interesting. So Cuba, see. All right, so let's start with RAID, because RAID is the first crack they took at this. And it actually was before the large data, big data science sort of phenomena started, but it was certainly the first crack at creating a redundant, replicated, secure in the sense of, like, if something went haywire, you still had a chance of getting your data back system that was affordable for the average person or the average company. It's fun telling these stories, and maybe you're sitting there laughing, and maybe you're sitting there thinking, "Shut up and just get on with the lecture." But since I can't tell, that's why virtual lectures suck. But anyway. So RAID, and this originally stood for Redundant Array. Redundant array of inexpensive disks. So RAID, RAID, was proposed by Patterson, Gibson, and Katz. At Berkeley. Or University of California in Berkeley, if you care, in 1987. Okay, so Patterson and Katz for sure, and even Gibson, super famous. If you've taken any course on systems, you probably use Patterson's textbook. I think they're all at Google now, of course, but whatever. So the goal here was to provide that high capacity, high reliability, and scalable, low cost storage solution. So this is the goal. I want to provide something that's big, reliable, that can be bigger whenever I want it to be, and I don't want it to cost a lot of money relatively. Okay? And so the obvious solution here is, so it was built from commodity PC drives. Okay. And back in '87, the drives weren't very big. They were in the megabyte size. And so they had to figure out how to use a whole bunch of these together. So they needed some sort of software system sitting on top of them to coordinate them. And that's the RAID part. And actually, this idea of using commodity storage solutions continues. So for example, Google's file system, GFS, which they use to store everything, as far as I know, is still built from just hundreds, thousands of commodity hard drives. And the system is specifically designed with the expectation that at any point in time, 15% of the drives will be broken. And so when it breaks, somebody walks out, pulls it out, puts a new one in, and throws the old one away. Okay? And so that's how these systems are built nowadays, is they're built from commodity components because they're cheap. And then the assumption is built in that some reasonable part of the system is probably going to not be working. And so the entire system has to keep working, even if 15% of it is busted at any given point in time. Okay, so that's a direct extension of this idea of RAID. So reliability was achieved. By arranging the drives in a redundant array. So of course we had backup in the day, and you can imagine where did backup occur? On DiskPack. But it was something that you had to set up yourself. It was something that wasn't necessarily convenient, and it was something that almost nobody did on a regular basis unless they were super scared about losing their data. So this was designed to do it for you without you having to do anything. And it was going to be done on this redundant array of commodity hard drives, not on some sort of specialized tape pack that every night read information. So what that meant is you got very good granularity in the time dimension. As you wrote information to the disk, it was redundantly being stored so that no matter when your hard drive failed, what you were going to lose was almost nothing at all. All right. So because it would have snapshots from the last write that you did. Okay. So today, RAID is actually now redundant. I don't know why I'm having trouble with this word. Redundant array of independent disks. See, look at that. Do I care? Oh, that's even easier this time. Independent disks. And it's a catch-all term. For dividing and replicating data across multiple storage devices. So there are different levels of RAID configuration that affect reliability, performance for both. So you hear about things like RAID 1, RAID 2, RAID 5. They all have different characteristics, and some of them are designed to improve reliability, survivability in the face of a disaster. Some of them are designed to improve performance, and most of them are designed to improve both. And if you're curious about, well, why did they change RAID from redundant array of inexpensive disks to redundant array of independent disks, you can guess, right? Who wanted this word change? The hard drive manufacturers. They didn't like the fact that they were called inexpensive disks. It made them sound cheap. And so when they formalized RAID, they said, all right, well, let's not use that word. Let's call them independent disks instead. Didn't make any difference. The system works exactly the same way. And by the way, Seagate, Western Digital, Hitachi, your disks are cheap, and that's a good thing because they used to be really expensive. I remember the first 1 gigabyte drive we bought. It was probably about $700 or $800 at the time. And I remember thinking to myself, why are we buying a 1 gigabyte hard drive? What could we possibly store on that to fill it up? Ha ha ha. Yeah. So now for our RAID array, we use Western Digital Reds, usually 6 gig. You can get up, like I said, to 8 gig. On some of these drives now that use something other than vacuum inside them to reduce the wobble of the drive and get an extra platter in there. And then if you're moving outside of that, we're talking, when we start talking about sort of future tech for disk storage, you're talking about much, much bigger maximum capacity than that. Okay. So RAID can be implemented either in software or hardware. Okay. And hardware RAID controllers normally present the array as a single, quote-unquote, virtual storage drive. And that makes the OS unaware of RAID-specific operations. Okay, so you can get RAID in software, RAID in hardware. I know macOS has RAID in software. I'm assuming that Windows also has it as well. But if you're serious, you're going to get hardware RAID. And the way it used to work is that you'd actually buy a PCI card or something like that and slap it into the chassis of your machine and then hook a bunch of drives up to it. Nowadays, you just buy a NAS, like a Synology or something like that, a QNAP, and it has the RAID hardware built into it, and then you just connect it directly to your PC using some reasonably fast interconnect. Okay. From the operating system's point of view, the RAID controller presents to the operating system like a huge drive, and so the operating system just sees a terabyte or a 10 terabyte drive, and it's like, great. And so that's why the operating systems all had to be updated. Their file systems had to be updated with larger, the ability to actually access larger file system chunks. So that was not trivial, actually, for a lot of the systems. So that they could actually work with these kinds of large virtual disk arrays. But they're all up to speed on that now. So, okay. So RAID offers 3 basic operations that would be things that we care about, different from whatever we get for a normal drive. One is mirroring. So data is copied to multiple drives. Okay, so whenever you write something to the disk, it actually gets written in multiple places. And if the system is smart, it's not writing it to the same drive, because when that drive fails, the whole point is that you've got redundancy, so you can grab it from another drive. So writing it all to the same drive would be stupid. The second is striping. So what happens here is that data is split over multiple drives. Okay. So the idea here is that when you're actually writing out or reading in the data, you can do it in parallel, so it's going to be faster than if you only had a single drive. And then the last operation is error correction. Redundant data is stored to detect and possibly correct data corruption. Okay, so redundant data means extra data. So you'll get some parity bits stored along with everything that you write. And those parity bits, every time you read the data, will be checked to make sure that the data is what it was when it was written. If it's not, it'll know right away, uh-oh, spaghetti-o, like we've got a problem. And if you're lucky, the parity bits can tell you how to take what you have and convert it back into what it should be. And if they aren't, then the RAID array will actually report, hey, sorry man, disk X is hooched. And so on most of these NAS systems, which are very nice, like if one of your disks goes kaput, either it dies or it's got some crap on it that it can't fix, you just reach in, you yank it out, well, the drive's live actually, you slam another one in, and it says, hey, thank you. And then you wait hours, and many hours later it comes back and says, I'm done, everything's back the way it was. And so it's not fast, but it's incredibly convenient. You just go off and drink coffee and have a nap or something, and when you come back, everything's back to the way it was. That's if it works in the proper way, and most of them do now, like Synology, QNAP are very reliable. We did actually buy a RAID 5 configuration from Dell, bad decision, this is many years ago. And so one of the drives went bad, and it wouldn't fix itself, which is the whole point of RAID 5. So I phoned Dell, and I said, hey, one of our drives went bad. And they're like, replace it. I'm like, I did. They said, wait for it to fix itself. I said, I did. And it came back and said, it can't fix itself. And they said, what? And I said, yeah, what? And so the guy says, wait a minute. And then he went away for many minutes. And he came back and he said, sorry, Matt, there's nothing I can do for you. And I said, what the hell? You sold me a product specifically designed to help me in this situation, and now you're telling me it doesn't work? And he was like, yeah, we don't buy Dell RAIDs anymore. For a lot of reasons, that's just one of them. All right. Dun, 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 dun. My second win now. I'm feeling a little punchy. Must be the meds talking. All right, redundancy. A new pen is achieved either by writing the same data to multiple drives, we just mentioned that's mirroring, or by calculating parity data. Such that a failure of one drive can be survived. either direct correction or correction over many hours, and that's the error correction that we talked about. Okay? And so there are various grade levels, as I said. Which define which operations are performed. So if you've ever been curious, so there's RAID 0. And so what happens here is that you get striking. The data is split to allow for parallel IO. So improved performance. No redundancy. No fault tolerance. Okay. And full drive capacities are available. Give me a few minutes here, since I started late, just to get through these, and then we'll be done. So RAID 0, not super popular. I mean, all it does is really make things faster, but if anything goes haywire, you're screwed. And it does give you the full drive capacity, though. So if you've got like 2 gig of drive, 2 1 gig drives, you're going to get 2 gig of virtual drive space. Okay. RAID 1, that gives you mirroring. So the data is duplicated over pairs of drives. So whatever you write to one drive, you write to some second drive that's paired with the first drive. So obviously here, you're going to get fault tolerance. And maybe some read performance. Because if you're reading things, 2 different things, you might read one from one drive and one from the other. Okay? And you get half the drive capacity. Because every pair of drives, one is the primary, one is the secondary. So if you have 2 1 gig drives, you only get 1 gig of drive space because you're duplicating the data. You need 2 drives to do that. There is something called RAID 3.4. I'm going to just tell you right now that that's striping with parity. So the data is split over 2 drives, and then there's a third drive that holds parity information for those 2 drives. And so that improves performance and fault tolerance. Okay? So you have the same thing as RAID 1, where you're splitting data over 2 drives. And then you also have this additional parity drive, this third drive. So you get 2/3 of the capacity of the drives, but you get some fault tolerance. And then there's RAID 5. That's pretty, RAID 1 and RAID 5 are the 2 most common types. So this is striping with parity. So data split over multiple drives. It doesn't have to be 2. So that's nice. And parity is interleaved with the data. So you still have a 2 to 3 ratio of data to parity. And so you can survive failure of one drive uninterrupted. That's the nice thing about RAID 5. So in RAID 5, if one of your drives goes down, you can actually yank it out, stick a new one in, and then in the background, it'll be reconstructing that drive while it's still providing full access to the data that you have stored on the RAID array. And so at some point, it'll be done. So then you don't really care about how long it takes to get that new drive up and running, as long as it does work at some point. So it can survive the failure of one drive uninterrupted. If you lose 2 drives, you're probably out of luck. Okay. All right, so again, apologies for starting late. Apologies for running late because I started late. Are there any questions about any of this before we leave for the day? All right, I appreciate your flexibility. I'll make sure to get Zoom working the way it's supposed to properly on Friday. And we'll talk a bit about parity, and then we'll move off RAID, and we'll move into some of the more recent hard large data solutions like GFS, HFS, Hadoop, and other things like that. All right, any questions before I end? Okay, thank you. I will see you on Friday.
Thanks.
Thank you.